I built a custom C2 channel that works completely over chess.com, and I'm going to show you how. A few weeks ago, I set a challenge for myself to build a custom C2 implant that communicates completely over chess.com. And I set some restrictions for myself. Firstly, all communication had to be over chess.com. Secondly, chess needs to be involved in the communication vector. It can't just be sending chat messages on chess.com or profile bios or something like that. And finally, the C2 must be able to send commands and retrieve the output from the victim PC. Here is a little diagram of what we're attempting to do. We have the Havoc C2 framework, which is an open source framework. We'll take a look at that just now. Communicating to chess.com through chess. And then the victim PC is talking to chess.com through chess as well. And this communication channel is the only communication channel between the C2 framework and the victim's computer. If you don't know what the Havoc C2 framework is, it's a post-exploitation framework which enables a hacker to control multiple computers to pivot and move laterally throughout a network, and it just makes working with a lot of computers all at once a lot easier. As you can see here, this is the client that a hacker would be using when connecting to the Havoc C2 framework. They can send commands and retrieve the output. They can see all the computers that they've compromised within the network and how they communicate with each other. And you can link these computers together so you can pivot through a network and through a firewall, and you don't have to communicate directly with every computer because each of the computers can be used as like a relay to jump through the network. And this amazing tool was built by Cracked Spider on GitHub. You should go check them out. And if you haven't used the Havoc framework, I highly suggest going to check it out. It's open source. You can edit it, you can contribute to it, and you can just use it for free. It's great. So here's a network diagram explaining exactly what's going on in the whole Havoc C2 setup. We have our hacker who uses the client to connect to the team server, and the team server is the central server which communicates with each of the victim computers. And the victims will have a little program running on it called an agent, which will then communicate back to the team server. And so the team server can then send commands and retrieve output. And the hacker uses the client to connect to this team server so that he can he can control what commands are sent and he can see the output. And this communication channel here between the victim computer and the team server is where we're going to be focused on during this challenge. So as for the Havoc C2 framework side of things, we can get a hold of Havoc C2 by just cloning the repo. Here we have it at Havoc Framework /Havoc on GitHub. It's a simple open source project. You just clone it. You build it with a make script, and then it gives you two binaries. One is the team server and the other one is the client. And you can just execute the team server like this with this command, Havoc server profile, and then you set your YAML profile file. I have debugging on just so we can see what's going on. And then we have our client. You just run the client binary, and that'll give you the connection details input form. You put in your details. I'm running it on local server, so it's 127.0.0.1, default port, default credentials. And then eventually you get connected to your Havoc C2 framework. So here we have the client. This would be the graph view where we get to see all of our victims. This is just the event viewer, so we have a log of what's happening. And then down here, this is where we would input commands and whatnot and see the output from our victim computers. As for building a custom agent, it was a challenge, but there were a few open source projects that really helped out along the way. Massive shout out to this guy, CodeXTF2. He made 2 projects and a really nice blog about interacting with Havoc through Python scripts. As you can see, he has this Notion C2 channel. That's a Havoc project. And he also has custom Havoc agent example. The Python project is like a really bare bones agent that interacts with the Havoc C2 framework. And this was a really good skeleton for building what I was planning to build. So in terms of actually building a custom agent for Havoc C2, there are a few pieces that we actually need. So there are 3 scripts. We have our handler, we have our listener, and we have the agent, which actually runs on the victim computer. The handler just sets some config and helps register the custom agent with the team server. So the team server knows what kind of commands it can run, the name of the custom agent, things along those lines. Also the magic number that the agent will send to identify itself. Then we have the listener, and the listener decodes the data from our custom channel and then sends it to the team server. And also when the team server wants to interact with the victim computer, it will send the data to the listener. The listener will then encode that data in our custom communication channel protocol and then send it to the agent. The agent, on the other hand, is pretty much the reverse of the listener. It downloads the data from chess.com in our example. It decodes it, then it'll execute the commands that it gets. It will then get the output from its system, encode that data, upload it to chess.com, then the listener will retrieve that from chess.com and then send it to the team server. So we need these three pieces, and that's what the project actually is. So now that we've connected all the pieces together with the handler, the listener, and the agent, we can move on to the chess.com side of things. So when it comes to actually interacting with chess.com in this project, there are a few things that we need from it. Firstly, we need to take a look at the site and find the communication vectors for storing data and for retrieving data. So here I am logged into chess.com with my Chess C2 bot account. Chess.com has a lot of features. I mean, if you just go to the nav bar on the side here, you can see how many different tabs and sections there are on the site. And there's even this little tools tab here that has a bunch of things that people probably didn't know existed, like this animated GIF maker, kids chess, chess timer, stuff like that. But there's a lot that we could use. There's playing chess online, like actually playing a live game against someone. And I guess you could friend two accounts and then play chess and communicate like that, but I think that would be extremely inefficient. So the vector that I chose is, if you go to train, you can go to analysis. And here on this analysis board, we can set up whatever position we like. And not only can we set up whatever position we like, but we can import it through this text format, and then we can store it in collections. So as you can see here, I have this yes sir collection, and we have 7 games in this collection. But the beauty of this is that we can then use chess pieces to encode our data and not really worry about what the chessboard looks like. And we don't have to send move after move after move and then eventually get blocked by rate limiting. So we're going to be using analysis boards as our communication vector, and then we're going to store those analysis boards in game collections. And the beauty of the game collection is that you can store multiple boards and you can make them public, which means that you don't need to be authenticated to actually download the data, which is going to help a lot for the listener and agent interaction. So we've seen what the front end looks like, but I actually want to take a look at the back end to see what the communication actually looks like between our browser and chess.com, because that's actually going to be what we need in our Python script. So if we go to our HTTP history, collections, we can see here, once you click on a collection, like the yes sir collection, it actually downloads all the data for all the games. And there's that string format that we were talking about being able to upload. And this is actually going to be what we need to encode data into chess. But we'll get to that later. So we have our storing and we have our retrieving. Next, we need to figure out how to authenticate to chess.com, because the issue is we could log in like in a scripted browser, like a bot, but there are mechanisms like Cloudflare and captchas and things like that, which are actually going to stand in our way. So instead, we're just going to use the token from chess.com. So we have this access token, and we can use that in our script to then authenticate directly to chess.com without having to go through the whole login process again. And thankfully, the access tokens on chess.com expire. I haven't actually made it to the expiration date, so that's fine. So that's going to be authentication. And then to maximize efficiency, this is not only to bypass rate limiting, but also to upload data at a sufficient rate that we wouldn't have this insane lag, even though we do have insane lag at the end of the day. We need to be able to upload multiple games and download multiple games all at once. I think in my repeater tab I have here. So we have upload game. This is the request that allows us to upload a game to chess.com through our script. And as we can see here, we have this text format once again. Fortunately, this request can take multiple games all at once. So we can upload a maximum of 100 games in one request, which is a lot of data, because if we work it out, we have 12 bytes of data per chess board, and we'll see why that is. But we have 12 bytes of data per chess board, and if we can upload 100 games at once, that's 1.2 kilobytes, which is not that bad, right? 1.2 kilobytes? Bytes, megabyte, kilobytes, bytes. Yeah. 1.2 kilobytes. I think that's enough for now in terms of a high-level overview of what we're trying to do. I want to get down to the real meat and potatoes. how are we going to encode data into chess? So before we get started, we need to take a look at our analysis board. On an analysis board, we can set up whatever position we like, but there are a few rules. Like if we clear this board now and then we say load, it's going to give us an error here. Cannot load position because it is invalid. Every position must have exactly one king of each color, and the side to move must not be able to capture the other king directly. So this is the minimum board. We need to have one king of each color, and the white king, whose turn it is to move, cannot actually capture the black king right now because kings can only move one space. But if we add a queen, you'll see this is not valid because the queen could instantly capture the king. And there is one other rule that is going to stop us. You cannot have a pawn in the back ranks. So if you load this, it's going to error out again. You're not allowed to have a pawn in the back ranks. But if you have a pawn here, load, it works fine. So there are limitations to the analysis board, but there are ways around it, and we can just restrict ourselves to these 6 ranks in the middle, which will prevent us from putting a pawn in one of the back ranks or checkmating one of the kings. So what data are we actually transferring across this communication channel? Well, I've abstracted all of the data that is sent by the team server to the listener into a base 64 string. So all we need to worry about is this one base 64 string, encode that into chess, and then get it across to our agent on the other side. And the agent will do the exact same thing, base 64. That's it. We just need base 64 to be encoded into chess. But how can we do that? Well, our analysis board can help us to encode data in a few ways. If you look at a chessboard, there are 6 pieces, but our kings need to stay where they are. So let's say we have 5 pieces. We have a pawn, we have a bishop, we have a knight, we have a rook, and we have a queen. I mean, we have 2 colors, but we don't want to checkmate the other king too quickly because then it would be an invalid board. So my idea to get around that was to have black pieces along here and white pieces along here, and starting with the black pieces because it's white's turn to move, which means that even if all the data here was queen, 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 white wouldn't be able to checkmate the black king, even though the black king would be able to checkmate the white queen. I hope you're following. We'll take a look at what the board looks like now. We have 5 pieces: pawn, bishop, knight, rook, queen. How do we encode data with our 5 pieces? Well, if you understand decimal numbers and you understand binary numbers, you'll be able to understand how we're going to do this. It's just like decimal and binary. With decimal, when you have a 1 in the ones place, you multiply it by 1. So it's equal to 1. Then you move it up to the tens place. Then you multiply it by 10, it equals 10. If you move that 1 up to the hundreds place, you multiply it by 100 and you get 100. It's the same thing with binary, which is called base 2. If you have a 1 in the ones place, you multiply it by 1, it's 1. If you have a 1 in the twos place, you multiply it by 2, it's a 2. If you put it in the fours place, it's 4, 8's place, it's 8, so on and so forth. But with base 5, instead of 10 or 2, it's just a 5. So 1 in the ones place is a 1, 1 in the fives place is a 5, 1 in the 25's place is 25, and so on and so forth. And so how can we actually calculate these numbers? Given a decimal number, how can we get the corresponding base 5? Well, let's see. We have a semicolon here, which is 59 in the ASCII number table. All we do is we divide that data by 5. So this would be 11, remainder 4. So then you put that remainder in the first position, 4. Then you move on to the next position and you divide that quotient from the previous equation by 5, which gives you 2, remainder 1. You leave the 1, you move on. Now into the 25th position. So you divide 2 by 5, which 5 doesn't go into 2, so it's 0, remainder 2. And you leave the 2 here, and you keep on doing that until you're left with 0. So 59 in base 5 is 214, but we're padding it with the 0 so that we can have easy to digest numbers in our chessboard. So to take that base 5 and turn it into chess, we just add corresponding numbers to each of the pieces. We have the pawn as a 0, we have the knight as a 1, bishop 2, rook 3, and queen 4. So 59 in base 5 in chess is pawn, bishop, knight, queen. And so here we see if we wanted to encode 1 semicolon into chess, this is what the board would look like. And as you can see, we're going to have 1 byte, 2 bytes, 3 bytes, 4 bytes, and it keeps going. we have a total of 12 bytes on the board, and we start with black pieces all the way up until halfway, and then we continue with white pieces all the way down. So that's how we're going to encode data into chess. We're going to use base 5 encoding and then corresponding pieces to those 5 characters. So we have our base 5 encoding, but how do we take that text and communicate it to the chess.com servers? How do we tell chess.com what position we want in our analysis board? Well, that's where Forsyth-Edwards notation comes in. It's just a text-based representation of a chessboard, or a whole chess position actually. It's pretty simple to understand. We have row 1, row 2, 3, 4, and so on and so forth, separated by slashes. Lowercase letters are black, uppercase letters are white, and numbers represent empty spaces. So we have a standard board here, and then all pawns, and then 8 empty blocks. Then we have 2 P1 capital N3, which is 2 empty, 1 black pawn, 1 empty, 1 white knight, and 3 empties. Then empty, empty, pawns, standard. The W here means that it is white's turn to move. This means that both black and white can castle on king and queen side. This means that there's no en passant on the board. This means that there've been no half moves, and this means that it is move 1, the very beginning of the game. So we're going to use this text-based representation of a chessboard along with our base 5 encoding to send chess positions to chess.com, and then we can retrieve those chess positions in the same format, decode the data, and we're good. And when you look at this Forsyth-Edwards notation, you can see it really lends itself to this base 5 encoding. It just uses letters like we've been using with our chess pieces. So we have a rook, a knight, a bishop, a queen. So we can just take our base 5 encoded string, break it up into sections of 8, and then put it into this Forsyth-Edwards notation, and we're good to go. So that pretty much brings us to the end of the explanation of what we're doing. And now we're going to get into the practical parts and actually put it together and see it in action. I've set up a simple demo Python script to show you exactly how the base 5 works. And all I'm doing is taking this base 64 string here, encoding it into base 5, encoding it into those fen strings, and then decoding it, and then you can see the original data coming back through the process. So here we'll run this Python script, go to the top. We can see this base 64, it's actually quite long, and it gets encoded into this base 5. And you can see bishop, pawn, rook, pawn, bishop, pawn, rook, 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 rook. And that's the representation of the original data in base 5. Then we break it up into those rows of 8, and that gives us 49 games. And then we can input it into this simple template, and you can see the black pieces, white pieces, and the empty rows with the king, because we don't want a pawn in those back ranks. And then white's turn to move, and none of this really matters. Then we can upload these games en masse to chess.com. Chess.com will store those in the game collection. Then our listener team server gets that information, and that's how the communication works. And then we take those Forsyth-Edwards notation strings, decode them back into our base 64 that we had before we sent it across chess.com. Now we're actually going to get into the demo of what I've built here, this Chess C2 custom agent. I'm here in this development environment. As you can see, we have our team server running, we have our client running, and we have this handler. This handler is going to set the config and let the team server know exactly what our agent is and what it can do. So we run it, it connects to the Havoc service, and we're all set up. So just to make things a little bit easier to see as the bots communicate with each other through chess.com, I made this data viewer application, and it will allow us to see exactly what games are in the game collections through the process. So we can see the listener send a command through chess, we can see the agent send the output through chess. It just makes it a lot easier to understand. So now we're going to execute the agent, which is the script that would be running on the victim's computer. Here we go, Python 3 agent.py. It's clearing the games, data viewer updated so we can see that there are no games in the game collection. Agent.py is going to collect some system information and upload that to chess.com. As we can see, there's a host name, we can see the working directory, and a whole bunch of other things. Now we're going to use the listener. The listener is going to download that data from chess.com. There we go, got data. It decoded the packet. Now it's going to send this registered keyword to the agent saying, you're ready, you're on Havoc, we're good to go. There we go, uploaded, registered. And now the agent is going to send a heartbeat asking for commands. every so often, and the listener is going to respond with either nothing or the command that we give it. So now if we go back to the Havoc framework, we can see that there has been an agent that registered to our team server. And this is the Python agent running on our computer right now. And we can click interact. And this is going to give us the opportunity to send shell commands and then to see the output. Now, this is where the demo gets real. And I know it's recorded, but it's janky. Sometimes it doesn't work. So shell who am I? A simple command. We can see that the listener got the command from our team server. And now it's uploading the data to chess.com. There you go. Who am I? Represented as chess. Then the agent is going to download that from the listener's game collection. And then execute the command. And then upload the response. So there's the data. Daniel, that's the username. Now the listener is going to download that data and then return it in our terminal. Take two. So we're uploading the command to chess.com. Who am I has arrived. The agent is going to download that command. And boom, as you can see, we retrieved Daniel, which is the username. Now the real challenge is sending bigger data over chess.com. So if I output something like etc password or maybe rpconfig, something like that, it's a lot of text. And so it's a lot of chess games. And you can only upload 100 at a time. We'll see how this goes. I've managed to make it upload in bulk, 100 by 100. And then eventually, once all the games are up there, the listener will download the data. But, you know, sometimes it just doesn't work. So here we go. Fingers crossed. So the command has been sent to the listener. The listener then uploads that data to chess.com. Boom. Cat etc password if config. Then on the agent side, we're going to see this is the output encoded as base 64. Clearing games is going to delete all this data. And there are 681 games that it needs to upload. So it's going to upload all 681 of those. As you can see, it's not decoding as base 64 right now because it's not a complete message. And then once all the games are uploaded, we should see the output. And boom, there we are. We have etc password and ifconfig all through chess.com completely. You saw the massive amounts of data flowing through this thing. It seems like magic to me. I was really stoked when I got this to work. It's super janky. I mean, the demo worked like once out of 3 times that I just recorded this video. It's not great, but I did set up an open source repo so that you can build something like this yourself. Instead of struggling to build a custom implant like I did for about a week, you can just go to this repo, you can download the Python files, and I've set up 2 functions in each of these scripts that just give you base 64 and they take base 64. All you need to do is communicate that base 64 across whatever custom channel you want to use and it'll work. So if you want to do something like this, feel free. Here's the source. And I've also uploaded the Checkmate C2 implementation so you can see exactly how this functions if you want to go and read the Python code or see any of it. I'm happy that you made it this far in the video. It was quite a long one. Stick around, subscribe. I'll be back. Cheers.